All right, well, see if this new microphone works any better. Good morning. How are you? I can understand that. Is that normal? Oh, I'm sorry. Hopefully it wasn't this class that caused it. You mean Twitch? Twitch? Watch the stream? No, I'm streaming it on Twitch, yeah. That's why I was kind of like, not streaming it on Discord. I suppose in theory I could, but I find that Discord streaming is kind of okay, but not great. Twitch seems to do a better job of it. Yeah, it's super easy. I mean, I was able to figure it out, and I'm old, so yeah, I've got like 30 people now following me on Twitch, which is great. If it hits 50, I don't know, Twitch does something. It's like it feels very social media-ish because as you get more followers, they change what you can do. And I'm like, okay, yeah, it's like I'm not sure why I care. I mean, but it is what it is. You guys sit in the same place each time you come to class? One of the things I've actually noticed, I've taught all over the world, and one of the things I've actually noticed that completely crosses cultural boundaries is this tendency for humans to sit in the exact same place. And part of the reason I've noticed is nobody actually owns a stake in their spot. So like I'm sitting there for a week, 5 days, and I'm teaching a seminar, and like sometimes somebody won't show up for the first day. They'll show up for the second day because their flights were screwed up or something like that. And they'll sit in a spot where someone else was sitting the day before, and you will actually watch the class reorganize, and then it'll go static again. It's really very fascinating because it's happened all over the world. And let's see, I never taught in China, but I've taught in Taiwan. I've taught in. Uh, Good morning. How are you? Singapore. I taught in India. I taught in France, Germany, Sweden. So, and it's very interesting to see these things that are so ingrained in human behavior that they don't really, because there's lots of things that culture affects, but there are still things like this sort of habit of taking the same spot each time, even though it doesn't make any difference at all. But if you didn't know that you were taking someone's spot, you would just do it, and then they would just simply adapt to it, and the world would just go on. And so I now make it a goal to go into class and sit in different places, just to see what it does. Sort of fun. And I'm a little bit of a troublemaker that way. Not as big a troublemaker as the person who started asking about details of the FLP proof last night on Piazza. I'm like, oh, there's a reason I didn't go through this in class. I mean, I just tried to get people to understand intuitively the idea, but if you really wanted the details, go read the paper. Because I can't imagine anything more boring than walking through a formal proof in a systems class. And this is like a joke in CS, is they just recently changed the graduate requirements. It used to be that it was required that all PhD students had to take one systems course and one theory course. And they've actually relaxed that like recently, in like the last year. And so what systems people usually dread most is taking the theory course, and what theory people dread most is taking the systems course. And occasionally run into somebody who likes both of them, and we all think they're weird. But you're in CS, so that pretty much goes without saying, doesn't it? And the clock is now officially working. I watched the guy come in, bring a ladder up, put a new battery in it, and have this long explanation about how it's not an official clock. And normally they would just simply mark it as that and not fix it. But he got his ladder out and got up there and changed the battery, and then gave me a long discussion, a description of his experiences in life. So 30 minutes he was here. Yeah, he just left because he had to go someplace else. But a very interesting perspective. One of the things he was talking about, and we were going back and forth on, is that the cost of acquiring something versus the cost of maintaining it. It is a very common issue that you will see in in tech. I won't say computer science, because computer science isn't programming. Computer science is the theory behind programming. But very frequently, management will only look at the cost of acquisition and won't look at the cost of maintenance. This is how you end up cutting corners in software engineering projects to do things that are expedient. It's like building your backup product and leaving the restore product until you actually have customers. If you're the customer that needs the restore product and it's not done yet, not so good. And for those of you who are watching the stream, wherever you might be, hopefully you can hear me. I switched microphones. Now I went to the next model up quality microphone. I wasn't willing to make the jump to the top microphone, because it turns out that buying a high-end portable microphone can be thousands of dollars. And they start selling all the pieces separately. Like even this one, it has a separate input. You can actually plug an external microphone into it, but unpowered. The more expensive ones, the ones a level up, then they start to power it. So you can use powered microphones. You know, like you see them when they're doing high-end concerts. They have the little glass tubes that come down. Those are even more expensive. It's like you buy just the transmitter set for $2,000, and then you buy microphones on top of that for another $500 or $1,000. Like, I like you guys a lot, but I can think of better things to do with 3 or 4 grand. They have all the gear and equipment here. They just don't have anything set up to actually use it the way that I'm using it for this class. So no, I'd rather rely on my own equipment and know how it works than try to fumble through this. It was like when they first told me it was going to be an 8 o'clock class, I said, okay, so that means if there's any AV problems, I'm going to have to figure it out, because there's no one who's going to be in the AV department at 8 o'clock in the morning. Technically, their hours of service are 7:45 onwards, like 7:45 a.m. to 7 p.m. or something. But the reality is, you're not going to get anything fixed at 7:45 in the morning. It's just not going to happen, because they're going to show up. The first thing you're going to do is go get their cup of coffee because it's too early. And see, I'm curious how class size is going to keep shrinking over time. And this is normal anyway, right? When I worked at Stanford, like the first day of classes, everyone was on campus. Everyone was there. And then after that, it would just start trailing off. And then by the middle of the semester, you were like, is this even the same place? Where did everyone go? I don't know. Anybody have any questions? We'll get started soon anyway. As long as they don't involve going through the FLP paper and explaining the proof. I have no problems with that. I'm hoping that other people will chime in and explain it to our that are going through formal proofs. Although, again, I stepped back and said, hey, let's talk about the intuition here. And my intuition is that the FLP proof works because it's essentially the halting problem in disguise, which is that halting in this case is reaching a univalent state, an accepting state, one accepting state where we've reached consensus. And since we know there's a point where we started, we knew we weren't in consensus. We ended, we know we are in consensus. Someplace in the middle, something happened that flipped it. Since it's a binary state, we simplified it down to that, right? There's a binary state here. We went from two possible outcomes to one possible outcome. So that means there is a single message that causes that. And since I'm allowed to hold that message arbitrarily long, no matter what you do, I can always come up with a sequence of messages that pushes that switch that flips it to a univalent state. I can always push that a little bit further. It's the ultimate in procrastination. Why do it today? I can do it tomorrow. And then when tomorrow comes, you go, it's like doing homework, right? It's not due tomorrow. I'll do it the day after. And you just keep repeating that process. And so we never actually have to, and this is where when you start looking at things that can be sort of extended infinitely, your brain kind of breaks down a little bit on them. Does anyone understand? Do you guys have a background in math enough to understand cardinality? So there are sets of infinite size. The real numbers are infinite size. The rational numbers are infinite size. The integers are infinite size. We can actually demonstrate that the integers and the rational numbers are of the same cardinality. In other words, we can create a bijection between the two of them. We can also demonstrate that we cannot create a bijection between the rational numbers and the real numbers. There's always more real numbers than there are rational numbers. And it's this very mind-bending proof. It's not super old in terms of mathematics. It dates from the 19th century. And there were people who for many years, and even today there are some, who disagree with the way the proof actually does that. They disagree with the fundamental method they use to establish this fact. But most mathematicians at this point accept that. When you do computer science, like in 421 where they study machine models, model of what a computing device actually is. And this was a real big question at the beginning of the 20th century that Dave Hilbert actually posed. And it was about figuring out the solvability of a particular class of problems. And then Gödel came along and said, actually, there's no way you can prove any of these interesting mathematical systems. And I'm being very hand-wavy here, right? So he formally said a mathematical system that fulfills these criteria itself will have propositions that can neither be proven nor disproven within that system. And one of the interesting problems there, since I was talking about cardinality, is are there any sets of cardinality between the size of the integers and the size of the real numbers? And it turns out you can't prove it either way. And so the fun part there is the moment you get something where you can't prove it or disprove it, you can create a system where you say it is true, and you can create a different system where you say it isn't true, and then you can see what happens from there. There's always these interesting questions that are not decidable. That one doesn't make too much difference for computer science. The halting problem makes a huge difference in computer science. Given an arbitrary set of executions, an arbitrary set of events, does this converge? Is in essence a restatement of the halting problem. Can you give me an algorithm that will, given an arbitrary piece of code, tell me if that algorithm, algorithm terminates? And Turing did this in a very concrete way, right? He said, I have states, and this is really appropriate because we're going to be talking about state machines today. I have states, and it was just about strings. I mean, it's super simple. I take the next character out of the string, and I look at that based on the state I'm in. I go to a different state. Well, this is just messages all over again. And what he said is, if that's the case, there will be strings. There's always a string where where I won't be able to determine. There will always be algorithms and strings where I won't be able to determine if that particular thing halts. And so the only way I can do it is essentially to run it. I don't know. Let's try it. And so the only answer you can get is yes. Because if the answer is no, you're never going to stop running it. And that is why I think that FLP ends up breaking down, because it's essentially set the exact same problem up, which is that we have an infinite number of possible orders of these messages, and we just keep narrowing the search space. But if you take the integers and you only take the even numbers, how many fewer integers do you have? It turns out you have exactly the same number, and it screws with your head. Because you're like, wait a minute. I mean, the Zeno's paradox. If I take an egg, I hold it 1 meter off the ground, and I drop it, we know that it has to go half the distance. So now at a half meter, we know it has to do it again. So now it's going to go to a quarter meter. And at a quarter meter, it has to do it again. Well, okay, so there's an infinite number of halvings. So it's never going to hit the ground. Let's try it. I didn't actually bring an egg to try it. But I'm pretty sure that everyone here has at some point or another dropped something similar to an egg and noticed that it actually does the same thing. Sometimes when you go to infinity, it actually converges. On the other hand, one of my absolute favorite sets is the Cantor set. So you take the real numbers between 0 and 1. And what you do is you take a third of them out of the middle. So now the set you have is the first third and the last third, but the middle third is missing. And we start by saying the measure, the size of how much is in that 0 to 1 interval is 1. Doesn't matter. It's an arbitrary number. In this case, we said the measure is 1. Measure theory, by the way, happens to be the basis of statistics. So we take something beautiful, we turn it into something horrible. The reality we live in. So now we have that new set where we got the first third and the last third, so the measure is 2/3. And then we repeat that process. And we repeat that process, and we repeat that process, and we repeat that process. And in the end, we end up with a set that has measure 0 and yet is still uncountably infinite. It has exactly as many elements in it as we had in the real numbers to begin with. Whoa. That's the problem with working with infinities. And FLP shows that it breaks down precisely because we've now got this problem, which is in infinity, things don't actually work the way that we think they work. So how do we solve this in the real world? We say, we live in the real world. We don't actually have to deal with infinities. We can actually say, we're going to make it finite. And our technique for making it finite was to say, we're going to put a time limit. If it doesn't halt within this period of time, we're done. And the moment you do that, you get rid of all the problems with dealing with infinity. It's not satisfying for the mathematicians, but when we're in systems, people actually want our systems to do something useful. So let's start with logistics, because that's more interesting than talking about FLP. Deadlines, the grades for project 1 have been posted to Gradescope, but I haven't been able to convince the learning technologies people to manually sync the Gradescope to Canvas rosters. So there's like a third of the class that it doesn't automatically do it. I'm lazy and don't really want to go and copy them all by hand, or write the Python script to download it from Gradescope, download it from Canvas, merge the lists, and upload it to Canvas. They'll either fix it or they won't fix it, in which case, if they don't fix it, then I'll have to write the Python script. I've done it before. It's kind of annoying. It's like, this is stupid. This integration works automatically. How could you people not make it work? I kind of wrote a flamey note yesterday to them about it. The reports, the TAs are kind of freaking out about grading it for some reason, so I have to go through several to explain to them what I want. I mean, basically, if you wrote a report for project 1, you're going to get it. So I wouldn't worry too much about that. Project 2, the code is pending. It'll be done next week. There are people in the class who have an extension, so I will wait until everything's done, and then the project 2 on-time grades will get posted on Gradescope, and then they'll eventually make it into Canvas in the fullness of time. Same thing with the reports there. TAs are going, oh, what do you want us to do? So I said, I could show you some examples of really good reports, but no, they wanted me to actually grade some of the existing reports, which I think is just their way of not actually having to grade them. And yes, I'm picking on them. If you do TA work, you should be used to that, right? The students will pick on you, the instructors will pick on you. It's just life. Any of you guys TA? Is that not the way it works? Yeah, pretty much. Hey, good morning. All right, project 3, 4, and 5 have all been released. They have staggered due dates. I saw one question about project 3. Project 3 is not too bad. Today's lecture is really geared towards what you're going to want to know about sort of the background for project 3. Project 4 is Paxos. Actually, when I put the syllabus together, I pushed Paxos further back than it is in the course at Georgia Tech. I moved things around because I thought, I'd rather actually have you guys look at simpler stuff than I dump the really complicated stuff at you. So the last several lectures have been pretty dense, deep, kind of like, oh my God. This lecture, I think you'll find a lot more straightforward. Not trivial, but a lot more straightforward. And the techniques we are talking about are actually pretty common. It's often the simple techniques that we use for solving a class of problems. Everything is due April 13th. Late projects have a 75% cap. I saw someone actually had submitted their project 2 a little bit late and got 75%. So it's all working, which makes me happy. If you're looking at alternate path 1 or 2, your initial proposal is due next Monday at 11:59 p.m. So, that means you can probably start working on it around 11 and you'll be just fine. There's no late due date on the project proposals. If you don't submit one, that means you're not doing one. If you are submitting one and you're doing path 1, which is a team project, you should all submit exactly the same thing. That's how I'm going to know that you have achieved consensus. We're all going to have exactly the same state. That way I know that you've all signed off on it, versus having one of you commit the other 2 to something that you were working on at 11:58 p.m. Does that mean? Yes. But I think it's fair. Let's see, and then you submit that on Canvas, blah, blah, blah. I think I actually have the hours for my office hours on Tuesday the same everywhere. Distributed consensus with a single actor is still hard. There's no required readings here. There's links to 2 papers that are about the techniques that we're going to talk about for chain replication. You're welcome to read those. I'm going to be describing them at high level here. Any questions? Anyone awake? I mean, I know it's Tuesday, right? This would be worse if it was Monday at 8 a.m. Any funny stories? I mean, I was sharing my funny story about the clock that's now working because the electrician came in at 7:15 and started changing the battery in it and then proceeded to talk to me for 30 minutes about it was an interesting conversation. I probably should have turned the live stream on at that point. He was telling me about his truck. Let's talk about a failure. The last time I kind of hand waved you, you said, we got all these different buckets that failures fall into, and it is true, but I'm going to go back to a real concrete failure. And this one is from a company called Cloudflare. Has anyone ever heard of Cloudflare? So a couple of no's and a lot of yeses. So Cloudflare is a company that does data replication to improve the availability of cloud services, amongst other things. If you have ever used the domain name system, Cloudflare actually implements a publicly facing domain name server that anyone can use that has high availability because it's geo-replicated, and it means that it's really fast, because what happens underneath the covers is that when you go to 1.1.1.1, that's its IP address for one of the DNS servers, it looks it up and it gives you a list of the places that you can actually go. No, the network, yes, looks at different places where it can actually send those requests, and it sends it to the one that's supposedly close to you. And this is all under the covers. You don't actually need to worry about that unless you're responsible for the network operations that make all of this magic happen. The reason Cloudflare exists is because the time it takes for you to load a web page depends on how fast we can get the assets that make up that web page. How long does it take to get an asset? How many assets are there on a web page? More than you think there are. How big are those assets? They vary in size from a few bytes to a few megabytes to maybe even gigabytes. So it can take a while. The farther away they are, how are we going to measure time or distance? How are we going to measure distance in the network? How do you measure distance in the network? I know how I measure it. I try to load a web page, and after about 10 seconds, I go, this is broken. So it's time. How long does it take me to get something? So distance in this particular usage case is really how long did it take me to pull that asset down? Because I need to have enough of those assets I can start rendering the page. If the page itself tells me how big the blob is, the object, then I can reserve space as I start rendering the screen. If I don't know how big the object is, how do I find out how big that ad is that I'm going to display? If I give you the name of something and ask you how big it is on the network, how are you going to figure it out? You guys are all really smart, so you're sandbagging here on me. Or you're just nervous because you think that, wrong. But this is now a real engineering question, and I'm going to stand here and keep asking it until one of you offers an actual answer. How would you figure out how big something is when all you have is a location for it, a name that you can use to fetch it? Go for it. How do you do that? I think you're overthinking this. Yeah. How are you going to do it? Wow, you guys really just don't want to brute force this, do you? Download it. When the stream stops, you know how big it is. Done. All right, so you managed to get me to give you the answer anyway. You're way overthinking it. Yeah, if you have the metadata, you're going to use it. But if you don't have the metadata, brute force it. Hey, this is my research. I spent a lot of time thinking about metadata and the fact that we have tons and tons of metadata, most of which we don't actually use. There's this guy who's still in systems and still very active named Jeff Mogul, and his PhD was on extended attributes. He didn't call them extended attributes at the time, but the idea was, hey, we can have arbitrary programs and applications add extra metadata to files. And here we are, 40 years later, and we still don't allow extended attributes on about like 70% of the storage system. And we certainly don't do it in any kind of uniform way. So guess what? No one uses it. If you ever use the curl interface, which is an easy way to grab content off of sites like Cloudflare, what you will find is that it actually has ways of getting the size through HTTP, but not guaranteed because the server may not provide it. And in the end, the only way to tell how big that is to download it. Now you have a definitive answer. When it stops sending you data, you're done. Simple. If I don't know how big the object is from the HTML on the page, I have to download the object to figure out how big it is. I can try querying. I can try getting the metadata. And you were trying to, where am I getting the metadata from? Well, in fact, the HTTP protocol allows mechanisms, or the HTML protocol actually allows mechanisms for determining what the size is, but they're not guaranteed. So I download it. Great. Now I have to wait until I download this damn thing so I can figure out how to actually paint the page. So now the time it takes for me to paint that page is going to depend upon the cumulative slowest time for all the things I have to pull off that page. I'm going to make this harder because I'm going to have assets that I have to download in order to figure out the assets I have to download in order to do the page. CSS. I'm going to pull other pieces of code into the page to render the page. So this keeps getting worse and worse. It snowballs on us. So the Cloudflare people, like the Akamai people before them and so on and so forth, have figured out that doing geo-distribution of commonly used assets is a huge win. Absolutely gargantuan win. And the reason this is important, and it actually dovetails with today's lesson, is because almost everything you download from the internet is static. It doesn't change very often. So it's what we call a read-mostly workload. That can be a blessing and a curse. It's a blessing because it means we can cache it. We can cache it really close. Your browser itself actually caches things. It uses disk space on your local device to keep track of things that you've recently downloaded because odds are you're going to need it again. Then there's going to be some material there that isn't easily cached because it is actually mutable. Those are like things where we query databases for things that are frequently changing or rapidly changing, in which case then the actual HTML you download is going to tell you, don't cache this. And now you have to fetch it each time. Well, the performance is going to suck more there. But we're still going to be able to use some of these geo-replication tricks to make things go faster because we're going to be able to replicate our databases. Cloudflare's business is replicating objects. So they are close to you. So your pages download faster. So you get better responsiveness. This is all distributed systems. Cloudflare is a huge distributed systems vendor. You probably don't even realize you're using it, but you are. There's almost nothing you can touch that doesn't go through Cloudflare or another service very similar to Cloudflare. So on November 2nd, 2020, so a couple years ago, these aren't old, but it's not like last week like I was doing earlier. They had a partial switch failure. It was a really cool failure because it wasn't complete. They had some things that were working in the switch in the control plane. So the link aggregation control was working. Link aggregation means that I have different connections and I bond them together and make them look like they're one bigger connection. They could potentially have different paths. They provide fault tolerance, high availability, load balancing. The border gateway protocol was working too. That happens to be the protocol that allows us to say, oh, you want to talk to 1.1.1.1? Here, we're going to send it this way. And there might be 40 servers that are all servicing that, but now it becomes geolocated. One of the interesting things I found when I was studying DNS behaviors is that if you actually start proxying through Chinese sites, your packets will take common names and go to different places than they do if you're outside China. And that's not unique to China. I'm sure the same thing is happening in Russia these days as well. Pretty much any place where we start to control where things go, we see exactly that behavior. You go to foo.com, and foo.com here in Canada goes to bar.com, but foo.com in, I don't know, Iraq will go to someplace else, maybe a black hole, maybe someplace in Iraq, maybe it goes someplace in China. That has happened. BGP has been used to route up to 60% of the world's traffic through China. Misconfiguration, they happen in the real world. Usually we notice fairly quickly because no one can handle 60% of the global internet's traffic flowing through their routers. Things break. But the virtual port control, which was how they actually controlled the ports on the switch, it wasn't working. And the data plane was dropping packets. So messages were not actually arriving. 1 minute later, etcd, which is a distributed database that uses the Raft consensus protocol, which we haven't talked about yet, but we will, begins to exhibit errors. And I've cut snippets of the actual web page that I linked to because they're very interesting in what they started to find. They're like, this is what we do, this is what happens when things start going wonky, but now we have a partial failure event. And this is where it started to get really crazy. And what was fun is they classified this. I love the write-up because they classified this as a Byzantine fault, which meant that they now had different copies of the same replicated database that were not in the same state. We've lost consensus, but people don't realize that, so they are still giving out what they claim are definitive answers, even though the answer is wrong. Well, that is kind of the nature of Byzantine fault. And they go on to explain, etcd goes read-only when it loses consensus like this, so we can keep things going, but we can't allow changes. And the problem is that etcd is heavily used for configuration data, so now your configuration can't change. And since your configuration can't change, now you start seeing failures in the clusters because they can't swap over. I have actually seen this in the real world. Not this particular failure, but similar failures. Many years ago, I was working with a company that was in late stage testing for a product they were about to release, and what they found was that they were doing disk reconfiguration on a single server. And they would send a reconfiguration message from I think it was on a cluster actually, so it was two servers sharing a disk. So they would send a reconfiguration message to the configuration service, but the message wouldn't arrive. And it turned out the reason was because all of the IOs that were going to the disk had been blocked. This was on Windows. They're all blocked in NTFS because these are asynchronous IOs, and NTFS has to do them in a thread. It just does them in a worker thread. And the pool of worker threads that got used there was also the exact same pool of worker threads that got used for doing loopback. So the messages weren't being delivered, not because there weren't resources on the computer, but because someone had chosen an arbitrary threshold that said, you can only have this many worker threads in this pool and no more. All those worker threads were waiting for that reconfiguration event to finish. In order for that to finish, a message had to be sent across this virtual adapter, the loopback adapter. So that it went from the storage service to the configuration service, but it couldn't be delivered because all of the worker threads that it needed one of to execute was blocked. They didn't control either of the two components. They had built a disk layer. They didn't control NTFS, and they didn't control the loopback adapter because those were both Microsoft's. You know how they fixed it? They built their own loopback adapter. They didn't use the same thread pool. And what's interesting about this is I have seen this kind of thread pool-based deadlock so many times in my career. I have a patent, actually, on building thread pools that don't actually experience this failure. I have a book that talks about these kinds of failures in engineering, and one of the cases they walk through is, I read it and I was like, wow, this is exactly what I've seen over and over again. Anytime you put a hard limit on something to try and prevent starvation, you create a different class of starvation problem. And I have literally seen this in my career many, many times. And this is just another manifestation of that. So this caused them to have to rebuild their database. It literally took, I want you to note that, this happened at 1445 and at 2120. So we are talking about almost 7 hours later, they have managed to rebuild their database. So they have been running in degraded service mode for 7 hours. And this is a global company, and their service degradation is affecting everyone on the global internet. Did I tell you this is about failure? One of the important things here that you may not be used to is that these companies have learned that you need to do postmortem analysis. You need to do it in a no-fault sort of way, because if you do it in a fault sort of way, you know what happens? People try to bury their mistakes. They try to hide what went wrong. Why did the space shuttle blow up? You're too young to remember that. I actually watched it, so I'm not old. That was 1987. After the fact, they did a very thorough analysis. I would say that aviation tends to do a really good job of this. Not perfect. Boeing definitely did a lot to try and hide some of the issues with 737 MAX. It's not perfect, but if you end up working in distributed systems, you have to build this kind of culture, because otherwise what will happen is that you won't do good postmortem analysis, people will try to bury the skeletons, and it'll happen again, guaranteed. Once you've seen a failure, you know it's just a matter of time before that failure is going to happen again. And you need to think of that instead. This is why I always emphasize this is about failure. So they talk about, and this is what I really want you to take away from this, the cascade of failures in this incident was interesting because each system on its own had redundancy. No system fully failed. And yet, they all entered this degraded state. And then everything just kind of melted down. And we'd never really considered this particular type of failure. I experienced this on my PC at home. I have this crazy 64-core Threadripper. And a 64-core processor generates a lot of heat. So I had a liquid-cooled unit. It goes to a large radiator, which blows air across this large radiator. And so it takes this fluid, runs it across the surface of the CPU, then sends the liquid up, and you blow air across it to remove the heat. Move the heat, very simple kind of heat pump, right? You're pumping the heat from the fluid into the air around the fluid. Apparently, it was very slowly leaking fluid. It was evaporating away. And so the temperature on the CPU started to climb. But while it was running, it wouldn't ever climb too high because CPUs that are built that have high heat generation have thermal safeguards within them. So it actually starts throttling. Until one day I noticed that I've only got 16 cores on my 64-core processor. And I start digging around and I'm looking at all sorts of things and I start figuring out, and I finally am like, maybe it's the AIO that's failed. And what was fascinating was all of the problems that resulted afterwards because of this slow heat buildup that got disguised by the system in the first place. So the downside to building things to be fault tolerant is it just simply means that the faults get harder and harder to find, diagnose, fix, and even contemplate. I'm now paranoid. I now watch the temperature on my CPU like a hawk. It sits at about 40 degrees Celsius. And then when I put my new GPU in, I of course put a water-cooled block on that as well. It's all part of a big system. And I haven't seen that go above 32. Now, anybody here know anything about GPUs? So the current high-end GPU is an NVIDIA 4090. And that's what I'm running on that. And it can run up to, I think, 90 degrees Celsius, 90, 95, somewhere in that range. And usually it runs in the 40s, 50s. I've never seen mine above 32. I just need to do better gaming, is obvious. The distributed systems community came back and they posted this in the article, and I thought it was interesting. They said this isn't actually a Byzantine fault. This is an omission fault, and it's like, okay, but it ended up manifesting as a Byzantine fault. So we saw Byzantine behavior, and that's what told us something went wrong. But the original cause wasn't Byzantine. It led to Byzantine behavior. I can see how they would make that mistake. But this is the other thing that's beneficial about making these things public. Now you make other people aware, and they can help you reason about what actually occurred. Today, we're going to talk about replication. Has anybody ever done a backup? He's willing to admit that he's done a backup. You know what the problem with backup is? Okay, so one or two people kind of half-assed hand, give a head shake. Has anybody here ever restored from a backup? That's the tricky part. If your backup systems work great, you won't really know if there's a problem until you try to do the restore. And that's when you find out that you're screwed. And guess what your recovery model at that point is? Good luck. One of these statistics they like to use, and I've seen it a number of times, is that a business that cannot restore operations of their IT infrastructure within like 10 days has a better than 50% chance of going out of business. It's really, really, really high. I had somebody in Boston was looking for an expert to talk about backup systems. And I've done a lot of backup work. I mean, when I started working at Stanford, one of my duties was backing up we had a couple of computer systems, and I was using 6200 BPI tapes, which you probably have only seen in movies. And those were 800 BPI tapes. So these were physical tapes. You went down, you mounted them on the machine, you ran the backups, you put them on the shelf, and you rotated through them. And we had a whole backup schedule. And if you wanted to know if your backups were working, you did a restore. And good discipline means you're going to do a restore once a month. There's rotation schedules and whatnot. And physical tapes actually die, actually wear out, because there's metal oxide on a piece of mylar film, and eventually the metal oxide flakes off and the tape doesn't work anymore. And you know what you do with a tape when it stops working? You toss it out. I suppose in theory you could recycle it. This was the US. In the US, when they recycle things, what they do is you put them in different bags and then they take them all and put them in the dump. We're going to talk about replication. Replication is backup. So how often do you do the backup? Let's say I do the backup once a week. And now my window of vulnerability becomes maybe once a week, maybe a little bit longer, because maybe my first backup doesn't work, but my second one does, because I've kept historical backups as well. Okay, great. How about if we take that time and we cut it down? Let's make it a day. Well, now my recovery window is much smaller. Is there a limit to how frequently we could back up? Essentially, there is a limit in that we can't back up faster than we can move the data. The cost associated with doing these backups increases as the time window decreases, because I have to spend more and more time moving data, probably data that's getting overwritten. If I only do it once a week, anything that got overwritten in that 1 week period, more than once, so you overwrite it 3 or 4 times, you only have to back it up once. When we actually do backups, we normally do what we call incremental backups. Occasionally, you'll do a complete backup of the whole system, but an incremental backup is the idea that I'm only going to back up the things that have changed since the last time I did a backup. And that makes the size of the backup much smaller. All we're going to say. It. Backups. The trick is, we have to get them right. Because if we don't get them right, we are not going to be able to recover from a failure. The techniques we are going to talk about today are all based on the idea that we want to have very small windows in which a loss can occur, to the point where we're actually going to, under the covers, make it take longer for you to do something because we won't tell you it's done until we have backed it up. And now, all we're really talking about is how we back it up. Oh, and of course, we'll hand wave restore because who needs that? When you're building your new backup software and you're going to sell it to the internet, you can always do the business savvy thing, which is don't develop the restore software. Just do the backup. Once you have paying customers, then you can go build the restore software. That really was sarcastic, in case you didn't get it. And sadly, there are business types who will and have done that. All right. The simplest way to achieve replication is to have two copies of something. If we're really smart, what we'll do is we'll actually allow clients to talk to either of those copies, because now we can load balance across them. And we could make this really simple, and we just simply hide the fact that there's replication going on under the covers. Is anyone familiar with RAID? You take two storage devices and you bundle them together into a mirrored set. That's the simplest form of data replication on a single computer system. Can you see any problems with that? Why store it once when you can store it twice at twice the price? Oh, and of course, as we build real computer systems, we begin to realize the only thing that fails isn't just the storage unit. It is high failure. It has relatively high failure compared to the actual controller, the storage controller. But storage controllers fail too. Been there, done that, debugged it. So now you end up building redundant storage controllers. And people put redundant power supplies in. And they put redundant, I mean, in theory, you can put redundant buses in. But at some point, this is going to go back to that whole idea of fate sharing, right? So I can have a disk drive fail independently of the other disk drive. I can have a disk controller fail independent of the other disk controller. But at some stage, so now I put redundancy into my power supplies. At some stage, I've got a CPU. Well, I could have two CPUs, I suppose. But there's always going to be some point at which these are fate shared. And we're not going to, this isn't going to fix that particular problem. We'll find other ways of fixing that problem. That's basically why we're going to talk about all sorts of other ways of doing backup. Because we're going to do geo-replication like Cloudflare did. Why would you use Paxos? Why would you use Raft? This is a really simple file, it's a really simple model of where we just simply replicate things. And we start breaking the fate of these things apart so that we can recover from certain classes of failures. It's all about the failures. Doesn't matter. Databases, files, file servers, virtual machines. The goal here now becomes making sure that a single failure of a node doesn't cause our service to go away. Somebody's paying us to maintain that service. The benefits of replication, remember this is just really fast backup. The benefits of replication are that we have fault tolerance, we have better availability, and we can even do scalability because we can load balance across them. Can you see any reason why we might not want to have 3 of something instead of 2 of something? So what does that mean that we have a problem with? What have we been talking about the last couple of lectures? Yeah, there you go. Perfect. So we need to make sure, and what was my definition of consensus? It was we all agree on the same value. So we're going to get rid of your incongruities by adding a consensus protocol in there. Okay, so now maybe it makes a little more sense why I went and talked about consensus. Yes? It's not writes that you load balance. It's going to be reads that you load balance. Remember, the whole Cloudflare example was that like 90% of the traffic is read. So you don't load balance the writes, you load balance the reads. We will be talking about load balancing in greater detail in a little bit, and it's going to talk about how we can optimize even some of the write cases, sort of. As we get into more sophisticated protocols, we will talk about how we can use quorums, for example, to achieve consensus without having full replication. We're just going to focus on replication today. So the load balancing here is just for reads, which is still like 99% of the win. It's a great question, though. If one of the nodes fails, we can just simply divert all of the traffic to the other node. And maybe that'll work. So let's talk about some models of replication. If I have a full read-write replica set, there's a question in the back. We're going to start really simple, and we're going to insist on our original definition of consensus. We will modify that definition as the class goes on. This kind of follows the actual evolution of these ideas. So that's one of the reasons why it's like I don't want to teach Paxos first, is because I don't want you to have to. I want you to have a model, and then I can like extend that model rather than give you the really complicated all singing, all dancing version of it, where you're going, what is going on here? So we're going to keep it simple. In fact, the real reason that you don't really want to do 3 is because it costs 3 times as much. So every time you add an extra replica into this, it gets more and more expensive. And so there are actually solutions that don't triple the cost. If you actually take 3 drives, we will have consensus mechanisms, just in disk drives, we will have consensus mechanisms that give us half of that 3 drive set is our capacity. So we get 1.5x capacity, even though we're using 3 drives. And when we go to 5, we're going to get 4 drives worth of capacity out of 5. And they're what are called erasure codes. And the erasure codes are just a fancy way of using information theory to encode data so that I don't need all 5 copies to reproduce the data. I only need 4 of them, or n minus 1. You can do erasure codes. That's a very specific case. In fact, erasure codes are given n copies and m portions of those copies, you can reproduce all of the data reliably. And so this becomes a balancing act between how much do I want to spend versus how much, how complicated do I want to make these protocols. Actually, we can use the same technique in security. It's very interesting. You can use something similar to an erasure code so that you have to have a certain number, access to a certain number of copies of a piece of encrypted data before you can actually decrypt it, which has a totally different goal, because security is not generally bounded by plebeian things like budgets. Security justifies everything. It'll cause you a lot of problems in distributed systems because distributed security is a real nightmare. Okay, so if we have 2 copies and we allow changes to either of those copies, we're going to have to actually replicate those state changes back and forth. This is possible. It's just a little more complicated because now it means that we have to deal with potential incongruities between the state here. We will be talking about these, but I'm going to simplify it in this case by saying we're going to look at even simpler models to start off with. Let's start with the simple ones, and then we'll build up to the more complex ones. A simpler model is where all of the requests go to one of the servers, and then that server coordinates with the other server to keep the data in sync. In the 1970s, there was this company called Tandem Computer that actually built hardware fault-tolerant systems, where literally on a per operation basis, per CPU level operation basis, they would execute and then go over to the other one and execute. And they would jump back and forth stepwise. These are still in production today. The company known as Tandem was acquired by Hewlett-Packard, and then when Hewlett-Packard broke itself up into multiple divisions, it remained as part of Hewlett-Packard Enterprises, HPE. HPE is still alive today. Non-stop computers are still alive today. They are incredibly expensive, and I know people who actually use them. Generally, the people who use them measure downtime of their services in hundreds of thousands to millions of dollars a minute. That's why they're willing to spend that kind of money. It's not hard to build these kinds of replication services. The challenge is making them fast. The safest thing here is that our first replica will never respond with an affirmative acknowledgement until it knows that the data has been recorded by both of the replicas. This becomes the visibility concern that we're going to keep coming back to over and over again in distributed systems. If the client doesn't know the outcome, they can't have done anything that relied on that outcome. The moment we tell them, yeah, it's done, they're going to rely on that. And that's going to affect their ability to recover from a fault. A variation of this kind of replication is, instead of replicating the state of the device or the storage, for instance, we replicate the operation. This only works if the operations are deterministic. If these operations are non-deterministic, this does not work. It's a different approach, but it's the same solution, same class of solution. Generally, when we start doing operations level work, we can do this with state as well, but we're going to do it with, we're going to look at the operations here. So we do the operations, we do it with a state machine. And what we call this is state machine replication, or replicated state machines, depending on how you like to say it. But it's the same idea, which is that what we're really doing is changing the state of this machine, then changing the state of this machine. And those two state changes have to be the same for us to know that what our state is equivalent. You can do it the other way, which is watch the disk drive. Okay, I wrote to that block on this disk. I'm going to go over here and write to that block on this disk. Those are both valid ways of doing it. The reason that we do state machine replication versus storage replication, low-level state replication, is because this is usually smaller. So this is a way of decreasing the amount of information that I have to transfer between the replicas. The cost of moving the data is something that dominates almost everything in terms of the performance of a distributed system. We'll see these kinds of techniques over and over and over again. And I know I've said this, and I will keep saying it. Moving data is the single most expensive thing we end up doing in a distributed system. No matter how fast we make it. The group that I work with at Georgia Tech, they're excited because ARM actually donated a bunch of machines for a cluster. So yesterday they were pulling the machines out. They've had these machines for like almost a year, but they had to get other hardware bits and whatnot. And so they're actually like pulling these machines out and starting to set them up. They're going to set 2 of them up because it's not quite ready to go into the rack. And they were installing 25 gigabit per second NIC cards. Like, wow. I wonder how much a 25 gigabit per second NIC card costs. It's about, ordered one for about $700. Anybody know what the fastest NIC cards are right now? Commercially available. 400s. The 800s are still not commercially available, but they will be soon. Actually, maybe they released one last week that I missed. The other fun thing about those is when you buy the cards, you actually buy the physical layer module separately. So that $700 for the card didn't include the copper or fiber modular plugin for it, which is probably more than the card. So for a couple $1,000, you too can have 25 or 50 or 100. Actually, I saw 100. 100 gigabits per second was about $22. Wow. I need to get that data between my computers faster. Those are almost bus speed. Even at those speeds, it still is our bottleneck. So the less data we have to send in order to replicate our state, the better off we are. That's why we do replicated state machine. The most common way of implementing this in a real system is that we create a log. The benefit of a log is that it gives us a serialized description of the operations that we have performed. So in fact, I don't actually have to do this a single operation at a time. I can do it in batches with a log. I can say, okay, take this piece of the log, send it to the other machine. The other machine can then replay those operations in the log, and now we know that we're consistent up to this state. So we can be working on things that are within a window where we might be inconsistent, and that's fine. This is a very common technique. It is well understood. I mean, I was not much older than you were the first time I actually had to implement one of these. They're fast. Made a huge difference. And this is an era where the biggest, most expensive hard drives were 1 gigabyte. And the big concern was that when you rebooted your Unix system and it came back up, it had to run FSCK to check the consistency of the file system. And on a 1 gigabyte drive, that could take 12 hours. Using a journal, an operations log just like this, I could recover that disk drive after a crash in less than a second. 12 hours to 1 second is a pretty decent performance improvement. That was like the biggest question people ask. Well, how long does it take you to check the disk? And I'm like, normally we just do it during the mount process under a second. And people just didn't believe me. But we could restore the consistency of the disk. That didn't account for media failure. You still have to actually do the whole physical scan and find all the data in the case of media failure. But that's the way that modern file systems actually work. It's a very powerful technique. We need determinism. When I put non-determinism into the mix, things don't work with replicated state machines. Because now I don't know that doing the same sequence of events or the same sequence of operations on two different replicas may not lead to the same outcome. So we've lost our consensus. So why would we use one versus the other, a state machine versus a replicated state machine, or state replica? State replicas are nice because we do single execution of the operations. The state can be large and scattered, however, so there are costs associated with that. Replicated state machines, we require that they're deterministic. That's not required in state replication because state replication is essentially, we don't know what these things represent. We just know that these blocks on the disk change, so we're going to synchronize them. That's it. So it's simpler from the perspective that I don't have to understand what the operations are. I just simply have to move the state changes. Log operations are often smaller. I mean, I've done very large log operations in 20 or 30 bytes. You have to run the operation a second time on the second replica. When we did state replication, we ran it on one, and we just copied the results in the storage to the other. So we didn't have to execute that command again. So we still get deterministic. I had never really thought of it that way, but that is true. We're getting deterministic behavior just because we only do it once, and we copied the results. You can use either of these techniques for primary backup replication, which is the simplest form of replication that we're going to be talking about today. But your choice there is going to be, like many things in systems, it's going to depend upon what the constraints are for the particular project. How fast does it need to be? How efficient does it need to be? I mean, if you don't care about budget, then hey, keeping duplicate copies, 3, 4, 5 copies of the same exact stuff, nobody cares. In the real world, what happens is you go to work for Google, and hopefully you don't get laid off, but you go to work for Google and you find something that saves them 2% in their data center. So we can buy 2% fewer hard drives. You've earned your bonus for the year. You probably have earned a promotion because you've just saved them $40 million. That's why people who work for Google in those kinds of positions where they can make that kind of impact can make $1 million a year. Because if you earned me $40 million, I'd be perfectly happy to share, let's see, not very much of it with you. But we're going to give you some stock options too, and that'll be great as long as the stock keeps going up, which unfortunately it hasn't. Oh well. Don't worry, we'll make you whole someday. Price will go back up. I don't know, anybody got a job at Google? Wow, they're falling down on they're falling down. I don't know what's wrong with them. So let's look at how we're going to achieve consensus in our replicated system. We have to ensure that we have consensus in our replicated system because otherwise we have kind of failed, right? If we don't have the same information on each of our replicas, then we've done something wrong. So we send messages, we acknowledge the messages, everybody does that, and then once our replicas have acknowledged it, then we can tell the client that it's happened. If the client's just doing a read, I don't have to talk to the replicas. I could talk to the replicas if I'm trying to be some sort of paranoid, make sure that I'm really giving them the right answer sort of thing. But assuming that we've already done our homework, our due diligence, and we know that all of our replicas are consistent, any one of them can actually answer it. A different technique or a different approach to this is what's called chain replication. In chain replication, what we do is requests come in to one of the replicas. If it's a read request, that replica can actually satisfy it. If it's a write request, then we have to send the message to the other replica. If I have multiple replicas, then what happens is we chain them. So the request comes in here, then it goes to the second one, goes to the third one, and then it goes back to the first one. So it has to go through the entire chain. And since this chain is actually a circle, go all the way around the circle. The problem you might be seeing now is, of course, this means we are getting more and more messages. And now we're going to start hitting that performance limit I was talking about. Now we're moving data across not one connection, but 3 connections. I'm thinking this might not scale quite as well as we want it to. It's actually not too bad. It's only order n, the constant. And in theory, we don't worry about the constants. In systems, we do. But we were doing it in parallel. Here we're doing it serially. But it decreases the number of messages we have. It actually does. It's not very good to try and demonstrate that with 3, but try and do it with 5. And as we're going to see, we can do better. So in 2014, a couple of researchers, so we're getting pretty current. This isn't old stuff. This is like within your lifetime now, right? So a lot newer. Within the last 10 years, these folks proposed what they called chain replication. They proposed this model of where what we do is we write, you can read from any of these, but you write to the head and then it propagates to the tail. I take it back. You read from the tail. That was it. So you read from the tail. You do writes from the head. You read from the tail because the tail is the last one to get the update. So if it has the update, then we know it is a consensus version of the data. So in other words, the way that we restore consistency here is we only use the guy who's last on the chain to answer any of the queries that are coming in. Because until it gets to him, it's not persistent, or them. Until it gets to the last node, it isn't persistent. Once it's on the last node, then it's persistent because now we've achieved consensus. And we just simply agree that as long as the tail doesn't say it's this value, it's not that value. And it'll make recovery a little interesting. It means when you recover, you're going to propagate from the tail back to the head. But that's fine. It's the way that you're recovering your journal. So the point here is because you're reading from the tail, if I find something that's not on the tail, then I say, sorry, it doesn't exist. Or if it's an old value, I say, sorry, it doesn't exist. Or it's the previous value, rather. Yes, right. That would be how we actually can handle a fault. So the question was, so if the tail fails, what happens? And the answer is, well, then we readjust and we change to a different tail. I'm not talking much about the recovery phase here, but hopefully as you're sitting there going, okay, so how do I add that tail back in again? You can see, okay, this gets a little more complicated, doesn't it? Because I might have to take the whole thing offline for me to fix it. Hello? Tell them to watch the stream. So what are the pros and cons of this? So this actually gives us a certain level of scalability, decreases the number of messages that we're sending per replication because we don't have to send acknowledgements back. We're only sending the messages forward. It does have good write throughput behavior. And we have strong consistency. But the problem is that read-only workloads are by far the most common. You see this over and over and over again. We write data once, we read it 19 times. It is literally that kind of a measure where it's like 20 to 1 sorts of ratios. That's just the web page rendering, right? Even the data that I'm pulling out of the database probably hasn't changed since the last time I queried the database. But maybe it has. Maybe I'm changing it. So we're going to try and do a little bit better with chain replication. And here's the interesting thing. This paper is before the other paper. So people continue to work on this stuff. But this is from 2009. And the other link that I gave you at the beginning of the lecture was about this paper. This was 2009. In this case, we allow reads to go to any of the replicas, but the writes propagate. The writes propagate, so we use the tail to determine. So what I do, let's see, I have a slide on this, right? So what I do is I maintain multiple copies of the data. When I read here, and it says, well, there's 2 possible answers, I say, damn, I have to go and find out if it's made it to the end of the chain. If there's only one answer, I don't have to go to the end of the chain to read it because I know that there's no other options here. It's just one possible answer. Great. Now I have a technique for dealing with this. And since most of the time these aren't in the process of being changed, this is a huge win because 19 times out of 20, there's only one value. But I have more messages to make this happen. So this gives me better read load balancing. In the case where it's in the process of mutating and I get a copy that says, well, maybe it's this, maybe it's that, I have to go and ask the tail. No, it's this. And now I can give the answer back to the client. When the client gets that change, they then have to update their state to say, this is now the master copy, and it goes backwards. And you can see why that works, because if it's the old value in the tail, give the old value to the client. If it's the new value in the tail, and you read it from one of the earlier replicas, it's going to say, I'm not sure which value it is. You're going to go read it from the tail. It's going to be the new value, and you're going to give that to the client. In either case, you always give the client a consistent answer. So we've achieved consensus. Kind of a choochie way of doing it, but we've achieved it. And that's really all that matters here. Here's the proof in the pudding kind of slide. This is what you presented at a conference to say, this is why you want to use my technique. Because, okay, so we're going to test it on 3 and 7 chain replica sets. So this is the normal chain replica 3. And we know that 7 is not going to be faster. 7 is going to be slower because it doesn't make the read case any faster. And it makes the write case slower. The benefit of being able to read from any of the replicas is that I can get some parallelism out of it. So I can get some improved performance. The more read heavy the workload is, the more performance I'm going to get. And so the reason they did 3 is they said, okay, so look, 3 is almost 3 times, maybe only 2 times as good as the basic chain replication was. Well, 2x is better. And it's not like I needed more resources to implement it. So now this is a big win. Same level of resources, better performance, even if it's only 2x, and I know that I can probably get better than that. And then when I do 7, I still get a benefit from this. So it's not just that 3 helps, it's that 7 helps even more. Again, it's not entirely linear, because you can see that 7 really drops closer to about, I don't know, level of 5. But it's still better than the 3 case. Question in the back. No. No. The question was, does this outperform in the case of high writes? And the answer is no. We are going to be able to find workloads where different choices behave very differently. And what you're going to find is that in a high write workload, crack is going to be worse than chain replication. Because crack is going to require that we actually access multiple nodes. Or at best, it's going to be the same performance. Because if you're doing high writes, they always go to the tail. Or they always have to propagate out to the tail. The reads come from the tail. So you wouldn't go above, I don't know why you'd go above 2, honestly, in that case, because it's not buying you very much. Unless you really you might do it for geo-replication or something. Solve some other class of failure. But no. And this is why I go back to earlier. The choice of your technique here is very much dependent on what problem you're trying to solve. And we will see this over and over again. High write workloads are rare, but not completely unheard of. Almost all workloads start out as power law distribution. They're big bell shaped, like that. What we do, I actually asked my first PhD supervisor about this at one point. He was here at UBC and he quit and went to work for Amazon for like 10 times as much money as okay. And I asked him, I said, how do we, so it was this observation that I made where it's like, okay, so we put all caching in all these layers to try and deal with this kind of high locality. And so what happens is that each layer below that, the curve, that power law distribution gets flatter and flatter and flatter until you finally get to the bottom. And at the bottom, you get what is the worst case for us from a performance perspective, which is we have uniform random. There's no locality anymore. So no more layers of caching will benefit us. And I'd never really thought of it that way before. And I'm like, is there a paper that actually points this out? That the way that you determine if you need another level of caching is to see if you still have a power law distribution. And if you do, there's stuff you can get by adding one more layer of cache. When you look at a modern computer system, caches occur over and over and over and over and over again. In a CPU, the L1 cache, and this applies to both ARM and Intel processors right now, probably RISC-V too, I'd have to go look, but I'm pretty sure. The L1 cache is the only mutable cache. So writes only go to the tail. It's weird. I'd never really thought of it this way, but this is exactly what it does. The writes always go to the tail, which is the L1 cache. It's small. The L1 cache then has to write back to RAM. The L2 cache is read-only, but much bigger than the L1 cache. When you look at a modern CPU, 60 to 70% of the total physical space on the die is for L2 cache. Yeah. Caches are a huge, huge issue here. L3 cache, which is typically one per processor. So if I have 64 cores, I've got one L3 cache, and I have 64 L2 caches, and I have on mine, I have 128 L1 caches because they separate instructions and data. And only the L1s are mutable. And then everything has to go back to the DRAM, and then it can get loaded into the other caches. Be that as it may, the point is that we keep squeezing these things out as we go through these layers, and that's kind of what we're doing here. So you can take extreme workloads, and you'd have to build a very custom solution to that. What you learn, though, is in the real world, those extreme workloads are rare. And usually you optimize just for that particular workload high in the stack. And as you go down further in the stack, you go to these more and more generic approaches to things that work across a broader range of workloads. So we talked about replication today. It's backup and restore. That's all it is. And what we're really talking about are the nuances of how we do the backup and the restore, and how we achieve consensus when we have multiple places that the same piece of data can be stored. When any of you use any cloud storage, one of my favorites is that they use a trick that I actually know the history of. When there's a conflict, like let's say you change a file and I change the same file, and so they both get backed up, and we can't tell exactly what the order is because we don't really have a good consensus protocol. So what you end up with is file conflicted with some sort of identifier on it. I don't know if you've ever seen this. It happens to me occasionally. It's like I worked on something on my laptop, I work on something on my desktop system, and it conflicts. And I actually know where that came from, where that model of reconciliation came from, because I worked on something called AFS, which was derived from the Andrew file system. And another file system that came out of that was called CODA. It was developed at Carnegie Mellon University by Satya. Everyone knows him as Satya, although his surname is much longer, has a very long Indian surname. He's a great guy, very, very smart. And he and his group did what's called disconnected operation, which is where in the old days you'd take your laptop and you'd like go sit on a train and you wouldn't actually have an internet connection. And if you take the train here and you use the internet connection, you'll still feel like you don't have one, but they'll tell you you do. And so the idea was that you could be potentially disconnected from the network for a long period of time until you got back together, and then it would have to reconcile. And basically, that was exactly what they said, is that if the file changed from two different sources, we're not going to change it. We're just going to rename it, and you get to fix it. And it turns out it's good enough. And everybody since then has adopted that. The guy who maintained the Windows version of CODA, I think he's still down at Western Washington University in Bellingham. And the reason I know that is because I worked with him because I built the file system toolkit that they used to build a Windows CODA client. And people still use CODA. It's crazy. Your best choice is going to depend on the workload, reads versus writes. Your system configuration is going to have a profound impact here as well. How many nodes do you actually have? How are they distributed? Remember, as I make the communications costs go up, this gets harder and harder for me to do. What are my consistency requirements? What kind of failures am I trying to protect against? This is what makes these hard engineering problems. This is what makes these hard systems problems. Because you need to now understand what the systems considerations are, and then eventually you're going to have to turn those into actual implementations. Any questions? My gosh, almost got the timing right on this one. Everybody's just like, eyes are glazed over. Oh my God, I've been listening to this guy for 80 minutes. Please just let it stop. Did it make sense to anybody? Sort of hand wavy kind of sense. Yeah, I got a couple of nods there, and I've got a question. Active replication is actually where, let's see. Active replication is where the replicas are kept in sync, and both can interact. Standby replication is where one of them is just sitting there as a warm standby, and so when the primary fails, you switch over to the secondary. That's the primary backup model. The backup becomes the primary when the primary fails. And this is a simple way of reasoning about things because consensus is defined by the primary. And we're going to see this approach. Essentially, the primary becomes the leader. And when we talk about Paxos and we talk about Raft, a lot of what we're going to talk about is how do we figure out who the leader is. In a primary backup situation, you get to decide. In a consensus-based multi-node configuration, we're actually going to have the nodes vote. And the usual solution that I saw used in the 80s was you just take the lowest IP address and you'd say whoever had the lowest IP address was the leader. And so when they failed, you'd have a new election and the lowest IP address would win. So it was really easy to achieve consensus on that. But that would be failover replication back, so you're going to fail over primary backup. All right. Thank you very much. And I'll see you next week. Hopefully it won't snow. Yeah, and then it's supposed to warm up. And it looks like snow right now they're predicting on Wednesday, but I don't trust weather reports anything more than a few days out. It's really hard to model weather when you're sitting next to an ocean. And that's it. We're done with the stream. And we're done with the recording.